This video shows how to get started with Gravity Engine 2. It assumes you've just imported the package and you have Gravity Engine 2 as a folder in your assets folder, and that the package dependencies of Gravity Engine 2, which are burst, collections, and mathematics, have already been loaded either by the asset store dependencies or directly. If you see compile errors when you start, it's likely that those packages haven't been imported yet. So when you get the package, it's structured in the way that Unity recommends. There's a runtime folder, which is where the code is. There's a samples folder, which is where the examples and tutorials are. And there's an editor folder, which provides custom inspectors for a number of the Gravity Engine 2 components. So we're going to start by looking in the samples folder, in the Getting Started folder, and I'll begin by just showing you what we're going to try and build by showing you the end result of the hello orbit scene, which I already had loaded. And so the purpose of the hello orbit scene is to just make the simplest gravitational system you can, which is a planet with a body and orbit around it. So if we look in the hierarchy, we have some things that are custom Gravity Engine components. We have a controller. So this is the main component that will evolve the bodies. And in Gravity Engine 2, the process of evolving them and the process of displaying them are separate so that you could have multiple displays. For example, you might want a world map of satellites and a 3D map of satellites going around the Earth. Or you might want to display only a subset of the bodies that you're evolving. That's all possible with Gravity Engine 2. So underneath the controller is a display component. And then underneath that, we have the actual gravitational bodies. We have a planet, which uses this GS body script that we'll talk about more in a minute. We have a ship, which is also a GS body, and its input is actually telling us exactly what orbit we want it to be in around the body. And if you look at the scene view, you can see that because we have a display orbit component also attached to this body right here, down at the bottom, we see a gizmo that shows us what the orbit is. And in fact, in the scene live, if we, for example, want to change the eccentricity, then that will take place in the gizmo orbit as well. So let's just have a look at what this looks like before we talk about in detail how we build it up and how it works. So we'll just press play. So you can see we have central body, the orbit. There's an element in here called a Gravity Engine 2 camera, which allows us to do some rotating of the views if we wish to, and some zooming in and out if we wish to. And those are pretty standard in all the tutorial scenes just because they're quite convenient. The other thing to note in the scene, all of the tutorial scenes have an object called GE2 documentation. There's a little text blurb that tells you something about what's going on in the scene. And there's also this very handy open documentation link. So let's see what happens when we do that. And we end up, sure enough, opening a web page with some documentation that talks about hello orbit and has a little bit of an overview diagram of how that works. We'll come back and look at this once we've built up the scene piece by piece, because then we'll have a bit more context. So let's go ahead and build a scene like that completely from scratch. And then I can talk through each of the components and what they're for as we go. So we'll do new scene. We'll create it. I don't need to save that. So we've now got a new scene. It's got a camera. We'll go ahead and just go into the prefabs and grab GE2 camera because that's just handy to use. And we'll get rid of the old camera. And then we just need to start creating some game objects to hold stuff. So we'll start with one that we'll call GS controller. We'll add the script of the same name. Now there are a number of choices we have here. It turns out the defaults are actually going to be pretty good for us, but we'll just walk through them. There's how we find GS bodies, how this controller will find its GS bodies. And the choices are either underneath this object in the hierarchy with an explicit list, or just scan the whole scene and grab them all. We typically use children because then we can group bodies underneath their parent controllers. There's an evolve mode chooser. So we can do everything in the main Unity loop, all the physics calculations. Or if we want to, we can select iJob late update, and then all of the n-body physics calculations, orbit propagations, maneuvers, collision detections, they'll all happen in a job that's separate from the main run loop. And then that job will be scheduled to complete in the late update method. We schedule it in the update, we complete it in the late update. For now, we'll just keep things as immediate. We have a choice of integrator, Leapfrog or RK4. For almost all things, Leapfrog's fine. And then we have a ability to control the tuning of the integrator by saying about how many steps per orbit do we want. So that's a nice scale independent way of talking about it, but of course it leaves open the question, well, what orbit? So that comes up next in the GS controller. So we have some things about scale here. We set a typical size for our orbit and the mass of the heaviest body in the scene. And we're going to leave those alone for now because we're going to take advantage of this auto set feature later. There's some other stuff down here that we don't need to worry about, but we will turn on debug keys. That means that we can time zoom by pressing 1 to 9, and we can press the P key to pause, go, and if we press D, we'll get a dump in the console of all the internal parameters of the physics. So that's the controller. Oops, didn't want to do that. So we will create another empty as a child, and we'll call that GS display. Add a component of the same name. Fewer things, similar choice for how we find the things we want to display. And the display mode XZ orbital plane. I'll come back and talk about that in a minute. And then the display mode direct or interpolate, that's for sort of fine tuning whether we want to move bodies to exactly the real runtime or whether it's okay to just let them go at the integrator granularity. And there's also the opportunity to set the display scale automatically, which is useful when you have solar systems or the Earth and the Moon, where the choice of the display scale might not be immediately obvious. There's a lot more about scaling in the documentations, and I won't go down that particular rabbit hole right now. So let's go ahead and create another empty one. We'll call it planet. And now we're going to add the component that represents a mass in Gravity Engine 2 called GS body. So the first thing we can do is specify a mass. And if you have something that's, for example, a satellite in orbit around a planet, perfectly okay for the mass to be 0 as far as gravity is concerned. And in fact, that makes the most sense because you don't really need to be calculating how much the satellite pulls on the planet. There is a propagator. We have a choice here. Gravity means we'll do n-body physics. Kepler means if we're orbiting around something, we'll use a on-rails Kepler evolution. P-Kepler is meant for on-rails around the Earth, and it involves the fact that the Earth is not round. SGP4 tells us how satellites move in a more complicated Earth model, which includes the fact that it's not round, has an atmosphere, there's a moon, etc. Fixed, which is in fact for the planet that's just going to sit anchored in the center of the scene, a good choice here. And then the final choice was ephemeris, which means it's going to move according to a table of values that we provide. So we're going to make it fixed. We're going to say that the input is going to be position and velocity, RV, in an absolute sense. And we're just going to let that sit at the origin. And that's all fine. And then we're going to add as a child of this, something called ship. And we're going to add to that a GS body. And this time we're going to use classical orbital elements, so that's what COE stands for. We're going to stay in dimensionless units. Well, let's make the orbit 25 units big. We'll give it a little bit of eccentricity. And so we now have a controller that will evolve a planet and a ship. And if we were to press play now, we wouldn't see anything because we haven't added any display objects. So you can do this. You can then interrogate the controller and ask it for the positions of the planet and the ship without updating the scene every frame. That's all fine. But we would like to see these things. So on the planet, first of all, we need something to see, so we'll add a sphere. And we might as well make that a little bit bigger, say 5 units big. And then on the ship, we'll just add a cube, just so we have something to look at. 1 unit is fine. And now we will go to the planet and say we want to add a display body. Automatically, it will assume that we want to track the attached GS body. The display body needs to be told what body it's representing. It might be the case that you had a whole second GS display component with a second GS display body, and then you would need to fill this in explicitly. There's some trajectory stuff, which we won't talk about in this simple hello orbit example, and there's some other optional stuff we can do with the display game object, which again, we'll defer for the time being. So we also need to, for the ship, add a display body. And it knows that it's the ship, and that's all good. And at this point, and notice now that there's a GS display body attached, in the scene preview, we've moved the body out to where it would be. So if we want to, we could at this point, let's just make sure our camera's looking at something. Seems to be looking at something, so we can go ahead and play. And there we have our body moving around the planet. We're almost there, but we're not able to see the orbit that it's in, and that's nice to be able to visualize that. So to fix that, we go to the ship, and we add an additional component called display orbit. This has automatically figured out there's an attached GS body, and that's the body we're going to track. We can not track that if we want to. It also automatically figured out that the ship had a parent called planet, and it assumed that that was the center. Now, the only other thing we need to do is make explicitly a line renderer and then tell ship that that's the line renderer we want to use, and we'll make that line maybe 0.2 wide. And now that we have display orbit in our scene, we're now getting the gizmo in the editor view. So now if we go ahead and play, we have our orbit showing up in the scene. Now, one of the things we stepped around at the beginning was how to actually scale this. So in Gravity Engine 2, we try and do everything in a way that relates sort of to the units in the scene. So if we say we want, for example, an orbit to take 30 seconds, then we can look at the orbit. We only have one body here. So if we do auto set, then it will automatically detect that the orbit scale should be 25 and that the mass scale should be 1,000. And then when we press play, it will be the case that by default, it will now take 30 seconds for this ship to go all the way around. And if you look at the GS controller info or inspector area, you can see there's some times here. We've got a Gravity Engine time, a world time, an elapsed game time, and Unity time, which is the same as the elapsed game time as long as you haven't paused things. And then if we want to press, for example, the 4 key, it speeds up and you can see the relative time speed up. I'll say just a little bit about scaling. There's a bunch of stuff about that in the documents. There are essentially 3 scales. There's the, if you look at a GS body, like the planet, we have a choice of units here. So we can choose to put in dimensionless, SI in kilometers, or AU. And that's what we call the world scale. Now, the goal in a numerical integrator in physics is to make sure that you have enough dynamic range. So you want to control the numbers, and typically you like to keep things around 1 for the average object. so that we're, for example, not putting in hundreds of millions of kilometers for orbit sizes and things like that. So there is a different scaling in the core, and if you look at in the console, one of the things that happens when it starts is it does a dump all. And if you look at the states, you will discover that the satellite, which is this body down here, is in an orbit that's sort of order 1. And we've also changed things so that the mass is of order 1. And you can read more about it in the scaling, but the other thing that happens in these physics calculations is we avoid multiplying by Newton's gravitational constant, which is like a crazy 10 to the minus 11 number all over the place. And we do that by scaling things so that that constant g equals 1. And you can read about those details in the scaling document. And whenever you're interacting with GS controller, generally everything is going to be in world scale units. The whole fact that the strange scaling happens in the GE core is not going to come up. And in GS display, the scale factor here is a mapping from world units to display units. Now, typically Unity doesn't like the transform values to be any larger than about 100,000, so you want to keep things below that, and you need to pick a scale so that even if you have, you know, 1,000,000 kilometers in your world units, you want to have the scale such that you stay within the 100,000 limit that Unity prefers. There is a box here for auto scale, so you could say how big you want your scene to be, and then you can say scan the scene for the object that's got the biggest distance, and it will work out that scaling for you. In terms of how this is actually running, we can go back to our little document here and have a look at this block. So there's a GS controller, there's a GS display, and then we have some GS bodies. So the GS controller grabs the information from the GS bodies, and then it creates what's called a GE core. So this is the kind of the wrapper on the core physics engine. And the GE core can be used independently and can be used without any reference to Unity, game objects, mono behaviors, update loops, any of that stuff. So it can be a standalone gravitational physics simulator. And that means you could go ahead and do what-if calculations and a little sort of AI side job to look at a trajectory. And that's exactly why it's architected that way. Within GE core, there's the GE physics core, which does the actual integration, propagation, and maneuvers. So a typical update cycle, the GS controller will tell the GE core how far into the future it should evolve the bodies. It will do that. If you're in update mode, it'll just wait. If you're in job mode, it'll schedule it. And then once that execution is complete, it will say to the display controller, okay, we have a stable set of physics values. Go ahead and display anything that you've been told you need to display and calculate any orbit paths that you need to calculate for rendering. And it will go ahead and do that. And there can be multiple display components doing that work. This does mean that if you're using job mode, it's possible there's physics churning away in the background while your code is running on the main Unity thread. If you need to get at information from the GE core, you need to add a callback to the GE core so that you get called once the core has finished its current evolution and has a set of stable values. So that's a quick overview of Gravity Engine 2. We did go down a few rabbit holes, but we did also show how to set up a basic scene and get something in orbit. There are many more tutorials showing some of the more advanced features of Gravity Engine 2, and there are videos available for all of those as well. As always, if you have questions, you can reach out to the support email in the README file. Have fun.